Hi students, welcome to lecture 72 in our course. Today I am going to discuss the concepts of plane stress and plane strain. And these two concepts are very important in the design of various aerospace structures. And at the end of today's video, you will know what are the stress strain relations, what are the strain stress relations for plane stress and plane strain. I am Dr. Ranjan Ganguly. So let us start at the point where we know that there is an airplane which is flying. If we take any point on the airplane, associated with that point there is a stress matrix, also known as a stress state, and this is a point property of the system. So this stress matrix is symmetric and therefore it has got 6 unique components, and we can also express this as a vector because we know that there are 6 components here. So this vector constitutes of 3 normal stresses which are denoted by sigma and 3 shear stresses which are denoted by tau. Now if you are unfamiliar with any of these stresses, I have made some previous videos where I have explained the directionality of all these stresses. So the next thing we figured out was that there is a relation between the strains and the stresses. So this relation is expressed in a matrix form for linearly elastic material. So remember, we are dealing with the linear portion of the Hooke's law, and this equation is essentially the three-dimensional Hooke's law, and you can see that in the complete general case, because this is a symmetric matrix, you are going to have 21 independent elastic compliances, and this constitutes an anisotropic material. Now you can count the values of A here, and you will see that there are 21 of these independent elastic constants, and in any general material these are going to be there. Now again, remember that the stress and strain correspond to a given point on an aircraft, and therefore what's happening is that at that point this relationship is giving you this particular matrix relationship, which is epsilon is A into sigma, where A is known as the compliance matrix, epsilon is the strain vector, and sigma is the stress vector. Now, fortunately for us, most materials are simpler than the general anisotropic case, and one level of simplicity is when you have orthotropic materials. These have 3 orthogonal planes of symmetry, and in this case you reduce from 21 to only 9 independent elastic constants. So in this case you see a lot of the terms in this matrix are 0, and so what we have is we have A11, A12, A13, A22, A23, A33, and then A44, A55, A66. So total of 1, 2, 3, 4, 5, 6, 7, 8, 9 elastic constants are there, or compliances are there for the orthotropic material. Then we came to the material which we often deal with in various mechanics of material books and in physics books also, which are the isotropic material. For example, aluminum, which has a property such that Young's modulus is 70 GPa and Poisson ratio is 0.33. And so what happens for the isotropic material is that the stress strain matrix looks like this. So here in the diagonal terms you have 1 by E for these 3 rows and columns, and you have 1 by G for these 3 rows and columns. So essentially, whenever you are relating normal strains to normal stresses, you have Young's modulus, and when you are relating shear strains to shear stresses, you have the shear modulus given by G. Now there is a relationship between E, G and mu, or Eg and nu rather, and that's given by E is 2 1 plus nu into G. So nu is of course the Greek letter which stands for Poisson ratio. Now you see the Poisson ratio comes in these diagonal terms, and this comes in the situation where you are dealing with the relationship between the normal strains and the normal stresses. So what happens is that while there is an expansion, say in the material, when you subject it to some tensile stress, there is a contraction in the y and z direction. So expansion in x direction but contraction in y and z direction. Similarly, if you have expansion in the y direction, you have contraction in the x and z direction, and so on. So this is the typical property which we observe in real material. Now, it's very important to remember that isotropic materials have only two independent elastic constants. This is a favorite question in many interviews and so on. And it's simply something which you can learn immediately if you look at this matrix for a long time. So now let's put everything in matrix form so things become simpler. We have expressed things as epsilon is A into sigma. So A was the compliance matrix. Now, of course, you can get the inverse relationship here, which is sigma is going to be some matrix C into epsilon. And by comparing these two, you immediately realize that C, which is the matrix of elastic constants, is going to be inverse of A. And this is something now we are going to try to find for this type of material. So what we need to do is, if we flip this particular matrix, we write the stress strain relation. We have to invert the compliance matrix here. So this is essentially something we have to do. Now, fortunately, this inversion process is not too complex. You can do it by hand, or if you have recourse to any symbolic mathematical tool, for example, you could use Mathematica, you could use Maple, you could also use MATLAB symbolic tool. So many people don't know that MATLAB also is able to do much of symbolic computation. You are going to get this as the stress strain relationship, and this is also nothing but the Hooke's law expressed in a three-dimensional form for isotropic material. And what happens in this case is that you get C11, C22, C33 as this equation here, E into 1 minus nu divided by 1 plus nu into 1 minus 2 nu, and also we get the off diagonal term C12, C13, C23 as E into nu divided by 1 plus nu into 1 minus 2 nu. Now C44, C55 and C66 are simply the shear modulus G. So these three cases are very straightforward because there is no Poisson ratio type of term involved here. The Poisson ratio only relates the normal stresses and the normal strains, and as far as the relationship between the shear stress and the shear strain is concerned, for the isotropic material it's a very simple relationship, and these relationships are given by these diagonal values C44, C55 and C66, which are equal to G. Now we are going to the main part of this particular lecture, which is looking at plane strain and plane stress. So let's start with plane stress, or rather plane strain first. And in plane strain, what we do is that we say that all the strains which have the z in them, we'll set them equal to 0. So essentially we are assuming that the structure is in some kind of uniform plane, that is the xy plane. We are interested in the xy plane strains and so on, and there is a particular situation such that the strains are something which we are not interested in and they can be set to 0. So this happens in cases, for example, if the structure is uniform in shape in the z direction, the loading is independent on z direction, and also there is some kind of restraint which is put on the structure. So what will happen then is that the terms here involving gamma xc, gamma yz, epsilon zz are going to be 0, and these terms are also 0. So essentially the strain matrix now simply becomes a 2 by 2 matrix, and if you think in vectorial terms, you are going to have only three strains, which is epsilon xx, epsilon yy and gamma xy. So two normal strains and one shear strain, because of course this is a symmetric matrix. Now immediately we can go to the stress strain relationship which we derived before in the general form, and we can get the stress strain relationship for the plane strain situation. So here you can see that the components related to tau yz and tau xc are going to be 0. But rather interestingly, there is a component present for sigma zz. So though we have set the strains to be 0, this sigma zz has manifested itself in this manner, and if you observe closely, you will see that this is related to sigma xx and sigma yy. Now, of course, if we look at the strain situation, the expressions for the strain and stress relationships are given here, and in this case, as you would expect, there is a epsilon xx, there is a epsilon yy, and there is a gamma xy, and of course the remaining strains which involve the Z factor are all set to 0. So that's the strain matrix for plane strain. That's by definition. So now let's just summarize what we saw in plane strain. We saw that the epsilon is defined in this manner. So it's very important to remember that this is a mathematical definition which we are doing, and then we are going to look for structures where this may actually be something which we can apply to. So it's very important whenever you are using plane strain or plane stress to try to use some kind of physical judgment as to why this condition should be applied. So all the strains involving the Z subscripts have been put to 0 here. But what has happened is that because of the stress strain relationship, we have ended up with the stress matrix which does contain a sigma ZZ. So though we were able to by definition remove the strains in the Z direction, we were not able to do that in the stress matrix situation. So somehow the stress has survived, and the stress is equal to nu into sigma yy plus sigma xx. Now of course this stress has happened because in this case the stress is happening because of the presence of the sigma xx and sigma yy, and the fact that the Poisson ratio exists in the real structure. So sigma zz is of course a dependent quantity. It exists because of the presence of sigma xx and sigma yy, and there is nothing we can do about it. So though we try to wipe out the strains in the Z direction, somehow the Z direction has manifested itself in the stress matrix. So now let's look at the plane stress situation, and in the plane stress situation what we do is that we define the stress terms which have a Z subscript to be 0. So this is the situation where these particular rows and column of the stress matrix become 0. So tau xz, tau yz, sigma zz, these become 0 here because they involve a Z subscript, and similarly these terms here become 0. So you get this reduced stress matrix. So now I have only a normal stress here, sigma xx, another normal stress, sigma yy, and a shear stress tau xy. Now plane stress is very useful in situations where you have thin panels subject to in-plane loads in the xy plane, and very often in aerospace structures you often use panels, so this is quite useful. The plane stress case is actually quite useful, though structures are not really completely in the plane stress situation because some remnants of these stresses are always there. But what we are assuming here is that these stresses may be actually very small and therefore they could be negligible. So this is one of those engineering decisions which is made so that the calculation becomes simple. Of course, in the old days when all the calculations were made by hand, this kind of reasoning was more important. But today you have access to computers, and so it may not be so necessary to make these approximations. So always remember that before you make any approximation about plane stress and plane strain as to whether it is justifiable for the given structure or not. So now let's get back to the strain stress equation. So the three strain stress equations for plane stress are given here. So here we have taken the previous equation for the compliance matrix and we have set those particular stress terms to 0, and so we obtain these equations here. So you get epsilon xx, you get epsilon yy, you get epsilon zz as the normal strains, and then you get the three shear strains here. Two of the shear strain comes out to be 0, but the third shear strain of course is here. Now do see here that the epsilon zz is actually related to epsilon xx and epsilon yy, and you can see that this relationship is given by this particular equation here. So very interestingly, the plane stress situation contains a strain matrix which has an epsilon zz present. So now let's look at the plane stress situation and let us write down the stresses here. So the stress strain relationships are very simple, and of course three of the stresses we have set to 0, so we can simply ignore that. And the stress matrix is the 2 by 2 matrix which you are very familiar with. If you are somebody who has studied mechanics of materials or strength of materials, you have seen these kind of stress states in various situations. For example, when you draw the Mohr circle and so on, you deal with these kind of stresses. And these equations for stress strain and strain stress are very important, because many of the problems which are often posed in various strength of materials books, they involve these kind of plane stress situations. So very often people think that only sigma xx, sigma yy and tau xy exist, and they are not cognizant of the fact that there are all these stresses in the z direction in many real systems. So that's something to remember, that plane stress is simply a special case of the real problem. So let's write down the equations again. So we saw in the case of plane stress that sigma is given by this 2 by 2 reduced matrix or reduced stress state, and you have essentially sigma xx, sigma yy, tau xy, because the remaining stresses have been set to 0. But in this case also, if you obtain the strain matrix, you get this epsilon z term which is present. So though you wiped out the stresses in the z direction or involving the z subscript, the z has somehow survived and it has manifested itself into the strain matrix. But remember that this is a dependent quantity. So here epsilon zz is dependent on sigma xx, or rather epsilon xx and epsilon yy, but it does exist. So this is telling you that there is an approximation being made here, and therefore the z direction still exists. So the real world is telling your equation something about the reality. So now let's look at composite materials, which are also quite popular as far as aerospace is concerned. So here again, if we take the plane stress situation, the equation becomes simple. And very often in composites we use this equation, because what happens is that composite panels are very popular, and these panels are typically parallel to the xy plane. And what happens is that you have the fiber direction along the x axis, and therefore in that particular type of panel structure we can use this composite stress strain relationship or strain stress relationship. Now here remember that there are four elastic moduli. So there is E1, there is E2, there is G12, and there is nu12. So we can express nu21 in terms of nu12, because the symmetry of this matrix is always there for the typical elastic structure. So this equation will hold that nu21 by E2 equals nu12 by E1. So that's something to remember. So in any case you are dealing with composite materials, you will need to get these four material properties, that is E1, E2, G12 and nu12. And once you get these properties, you can get the relationship between the strains and stresses of a composite material, which is typically a panel. Now if you invert that matrix and do some algebra, you are going to get the relation between the stresses and the strains. So again remember, this is plane stress. So there are only three stresses here, sigma xx, sigma yy, tau xy, and there are three strains here, epsilon xx, epsilon yy, tau xy, and I get this matrix here. So as far as the shear stress strain relation is concerned, that's very nice. It only involves G12. But as far as the relationship between the normal stresses and the normal strains are concerned, I have a plethora of terms here. So I have E1, I have E2, I have nu12, and I have nu21. So again, you need to get all these information, all these numbers, and then you are able to get the relationship between the stress strain for a composite material. So composite materials are not very much different or difficult, I should say, compared to isotropic material. It's just that they have more material properties, and therefore you need to consider all these material properties. Another challenge of course is to try to obtain these material properties. Typically they are obtained from experiments, but they can also be obtained from various computational material science simulations. So again, that's an active area of research and is very important. So to summarize, we will say that plane stress involved the case where three of the stresses were set to 0. All these stresses involve the z subscript, because we always prefer to deal with the xy plane. That is our typical mindset. And so these particular terms here are set to 0, which is this row and this column, which involves the z coordinate direction. In the plane strain situation, what happens is that we set all the strains which involve the z to be 0. So that leads to these three terms here and these three terms, or rather I should say this row and this column, being set to 0. We also saw that just because you set all the stress term to 0 doesn't mean that all the strain terms become 0 in the strain matrix here. The epsilon ZZ term survives but is dependent. And also we saw that in the plane strain situation, though we set all these strain terms to 0, the stress term survives in the matrix, that is the sigma ZZ term. And this epsilon ZZ and sigma ZZ term remind us about the existence of the Z coordinate in the actual real structure. So like I mentioned today, the plane stress, plane strain concept is very important, specifically in strength of materials. People can visualize many things in the two dimension. You can draw many figures in the two dimensions, such as the Mohr circle and so on. And therefore, a lot of the strength of material books cover a lot of things about, especially the plane stress condition, which is also the more useful of the conditions. But do remember that nowadays you deal with everything computationally. So later in life, when you are dealing with software, maybe you are using COMSOL, you are using ANSYS, you are using Nastran, you are using any of the typical software which are used in structural analysis. You can get the complete stress state. There is no problem with that. And when you do all the calculations, if the Z direction strains or stresses come out to be small, it doesn't really matter because your system will take care of it. And you never know what kind of loading will be there, which may sometime cause these stresses and strains to become larger. So in general, if you are dealing with real life problem, it may not be very useful to consider these particular plane stress and plane strain assumptions. But in case you are dealing with problems in class, in case you are dealing with problems for which quick solutions are required, you can do very well with plane stress and plane strain, because in that case you will get the solution very easily without resorting to all the cumbersome math which comes by dealing with the three-dimensional stress strain relationship. Particularly we will see certain things such as compatibility conditions, which we will discuss in our next class for strains, are very simple if you are dealing with plane stress, but if you are dealing with the 3D problem, you encounter very complex set of equations for many of those things. So many a time, many of the books in aircraft structures and solid mechanics like to explain things in terms of the plane stresses. Professors like to write equations which are easier in the blackboards or the whiteboards, and therefore plane stress is very ubiquitous as far as education is concerned. So I'll end this video now and I will see you in a lecture sometime soon. See you then.